calculated the variance of this quantity, the variance of this prediction for a future value, we can construct a confidence interval, the same that we've done previously. So the confidence interval is just going to be the y hat, this y hat naught, or this predicted value for an individual with those particular x values or predictor values, plus or minus t star, which that t star is just from our t distribution. It's going to have n minus p plus 1 degrees of freedom. It's going to be at the alpha level, or the alpha over 2 level if we're doing a two-sided test. And then it's going to be multiplied by the square root of that variance that you just derived. And so the square root of that variance is going to be sigma squared, or sigma hat rather, times the square root of 1 plus x transpose, or x naught transpose, times x transpose x inverse times x naught. So this is going to be the confidence interval for the prediction of a future response, which colloquially we often call a prediction interval. And the reason we call this as a prediction interval is because it actually behaves differently than a confidence interval, a traditional confidence interval does. And why is that? So there's a very important conceptual difference here. Parameters like beta 1 and beta 2, these are considered fixed but unknown. So they are not random, which I think we've covered this in a lot of different ways because, for example, when we've been taking expectations or variances, we treat those beta values as fixed, which is why we can kind of pull them out of our expectations and things like this. So they are fixed but unknown. So they are not random. And another way you can think about it is that if you go back to sort of thinking about what makes something fixed versus random, and thinking about why, when we had like x, for example, was fixed, but y is random because y equals x beta plus epsilon, and epsilon is random. And when you're adding a random variable in, it makes the whole quantity, if you're summing it in, it makes the whole quantity random. So anyways, the fact that parameters like beta 1 and beta 2 are fixed, that's why we interpret confidence intervals around beta the way we do. So confidence intervals for parameter estimates, confidence intervals for the beta estimates that we've been talking so much about, those are interpreted as, if we were to repeat this sampling procedure many, many times, it's the probability that the true value will fall within the intervals calculated is going to be 95%, for example, with a 95% confidence interval. And it's not the probability that the true beta value falls within the actual values calculated, because the true beta value is fixed. And so that is either going to be inside or not inside the confidence interval. There's not some probability associated with that. So the reason we kind of think about confidence intervals the way we do is because we believe that these beta coefficients are fixed. They just happen to be unknown. A future observation, on the other hand, is a random variable. And so this is an important distinction. And why is a future observation a random variable? Well, I'm going to skip back to when we were talking about what this actual value is. But it's going to be x naught transpose beta plus epsilon. And so remember, when we're adding in some random component, when we're adding in something that's random, then the summation of that is going to be random. And so because we're adding in this epsilon, this ends up being random. The prediction of a future value ends up being random. And so the fact that this future observation is random influences how we think about the intervals calculated around it. And so this prediction interval that we just calculated, the prediction interval, the way you interpret that is the way that I think people commonly try to interpret confidence intervals, which is the incorrect way to interpret a normal confidence interval, but it's the correct way to interpret a prediction interval. So because the future observation is random, or the thing that the confidence interval is pivoting around is random, we can say that there is a 95% chance that the future value falls within this interval. So I'm going to say that one more time. The reason we can make the statement that there is a 95% chance that the future value falls within this interval is because the future observation is a random variable. And so you can make probabilistic statements about that value falling within a certain interval with some probability. So in the confidence interval case, The thing that's random is the confidence interval, not the beta coefficient. Beta coefficient is fixed, so we can't say anything about the probability of that beta coefficient falling within certain values because the beta coefficient just is, the true coefficient is just a fixed value. But the future observation is a random variable, and therefore we can say things like there's a 95% chance that the future value falls within this interval. So just to reiterate, because we've spent so much time on confidence intervals and we just had a whole recap on confidence intervals this week, I want to restate that this is not the correct interpretation of a parameters confidence interval. It is the correct interpretation of a prediction interval. So there's a distinction here, and the reason this is the correct interpretation of a prediction interval is because the thing we're calculating that interval around, that future observation prediction, is random. So coming back to our original kind of discussion about these different intervals, this first one is the interval for the mean response. This is like the normal confidence interval that we're used to. This is a confidence interval for the mean response. This is a confidence interval for the predicted response, or also known as a prediction interval, like we had discussed before. And by confidence interval, I mean these are the variances for each of those. And so which of these is going to be larger? Well, you can think about, as I mentioned, the variance for a mean response is going to be smaller than the variance for a future observation for an individual. And intuitively, I think that makes sense because you would think that, if you think about what a variance is measuring, it's measuring kind of deviations that you expect. And if you're looking at something on average, you'd expect that the averages will have smaller deviations. Versus if you're looking at just one individual, you would expect that a single individual is going to have a larger deviation to be expected than a deviation from the average. And so you can see kind of directly how this number is bigger than this number because there's this 1 plus here. So basically we have an extra sigma squared if we distributed the sigma squared to this part of the equation and to this 1 here. You'd see that you're adding an extra sigma squared in for the prediction interval. So those are necessarily going to be larger.